Okay, today we will start the review. We have today the first two chapters, which are the rotational kinematics and rotational dynamics. I have many questions. These questions are not related to the exam, okay? So the exam, there's no questions like this in the exam. It is just a general example. I will not, I will see, maybe I will prepare some formula sheet and I will put it for you as a PDF file. But you can use the formula sheet. One formula or many sheets from the formulas. There's no need to use your book because you don't have the time. The exam will not be open time. It will not be open all the day. Just you have, I think, 2 hours to finish it. Now I just finished 23 questions and I will put more also. I put 2 or 3 extra credit questions. What else? Yes, the exam is not comprehensive, but you will see this material depends directly or indirectly on the initial one. So you need to know how to calculate, to convert between units, how to calculate the velocity, the speed, and the force, and so on. What else? If I have any notes, then I will tell you about them. Finally, if you have any missed or late assignment, please, you can do it, or quiz, or even evaluation. The evaluation is a quiz. So finish everything, please, before Wednesday. Now, I will start the first question. I put now the first review file, which is about rotational dynamics and kinematics. Tomorrow, you will see another file about selected topics from the final chapters. We will start now. Any question about the final, about anything else? Now, you have this question, but you will see also another kind of unit. It is simple for you. Now I need you to convert it from radian to degree. It is, I will solve just 1 or 3, 2 or 3 of them. The rest is will be simple. Keep in your mind that each pi radians is equal to 180 degrees, which is this angle. And pi is equal to 3.14, which is 22/7. It's just a number. So if you need to convert from a unit to unit, you need to multiply by 1, which is the coefficient of convergence, which is, in our case, even pi radian over 180 degrees or 180 degrees over pi radian. Just see what you need to do and be careful about your calculator. It should be, I think, most of our calculations from now on are in radians, okay? Not like the previous material. I told you we will deal with degrees. Now we will deal with radians. Now I will solve the first one. I need to convert 45 degrees to radians. So I need to multiply by 1, which is one of these ones. I need the degree to be downward to cancel it with this degree. So it is 180 degrees multiplied by pi radian. So it will be 45 multiplied by 3. It will be 45 pi over 180 radians. So it will be 45 pi over 180. It is 0.6 7, 8, 5, and something. Okay. What about the next one? Pi over 6. It is a radians. I need to multiply it by 1. And this one can have the radians in the denominator. So I need the degrees upward. So it is 180 over pi. In this case, it will be pi multiplied by 180 over 6 multiplied by pi. It is in degrees. So pi will go with pi, 6 with this, it is 30 degrees. Okay. For example, I can solve this 1000 degrees. A 1000 degrees is more than one rotation, many rotations. I need to multiply it by something degrees here, which is 180, and pi in radian. Simple, just like the first one. It will be 1000 pi over 180 radians. So it's simple. Shift 1000. Where is it? This here. It is 17.45 3 something radians. Is it simple? Do you need more question? More one? It's okay, you can complete this by yourself. Okay. The next question. As I told you, I'll put some, or there's some concept questions, which are just matching or true false. Okay, now we have the relations. Question number 2, we don't have any relations. Let's put, we have a rotational motion. If you download the PDF file today early morning, you will not see this because I correct some mistake here. A spot of point on a bicycle, circle. There's a circular on a bicycle, and there is a point, a spot point. It was 29 centimeters. I removed the 9, and it is just 20 centimeters. So R is equal to 20 centimeters. This point is rotating. Okay. This point in its rotation, okay, its linear distance, this rotation, if we have it as x or s, which is a linear distance, it will be equal to 2 meter 65 centimeters. Okay. You remember that if we have this section S from this circle with an angle theta and radius r, S is equal to r multiplied by theta. Now our S, it is not a section, it is more than one rotation. This is S. Okay. I gave you S and I gave you R. I need to find theta. Theta will be in radians. If you like to convert it to degree, it's your choice. So theta is equal to S, this is S, is equal to S over R, which is equal to S. You can see I consider everything in meter. 2.65 over 0.2. So S theta will be equal to, let me see, 13.25 radians. Simply. This is the speed or velocity law. You know that the velocity is equal to x over t. No, it's the same. Just we have three parameters. Theta is equal to S over R. I didn't give you her time to compute any velocity, okay? Now we have equations of motion with constant acceleration. We apply this many times in linear motion. Now we need to apply it in circular motion. We have this relation. Theta is equal to 8t minus 2t squared. We have these relations. You can see them here. We have omega is equal to omega naught plus A or alpha t. We have the alpha. Omega squared is equal to omega naught squared plus 2 alpha theta. Theta is equal to theta naught plus omega naught t plus half alpha t squared. Theta naught is 0 in our relations. You can name this omega 2, omega 1, omega 2, omega 1, omega finally, omega initially. You can compare them with the linear motion. Omega is the velocity, alpha is the acceleration, t is the time always, and theta is the displacement. Here, I am asking you about many things. First, we need to compare this with one of these equations, as you can see, it is the third one. Okay, the first thing, what is the initial angular velocity? Omega naught or omega initially. What is it? Comparing, we don't have theta naught here, it is 0. How much omega naught? It is the argument multiplied by the time. So it is 8 radians per second. Simply. 2. What is the acceleration, I think? Angular acceleration, yes. We have there t squared. And we have half alpha, it is equal to, we have half alpha equal to minus 2. So alpha is equal to -4 radians per squared second, right? Is that clear? Because look here, we have this is equal to half alpha. I will write it here to make it more simple. Theta is equal to omega naught t plus half alpha t squared. Just like that. What about the third requirement? time when the rotation stop. Look, now we have initial velocity, which is 8. The acceleration is negative, means that our object will stop after a while, right? Now we need to find the time when the rotation stops. So you can use one of these. Now we have the acceleration, we have omega 1. We need to find the time, so we can use the first one. Just as what we did in linear motion. We have omega 2 is equal to omega 1 plus alpha t. Omega 2, after stopping, it is 0. Finally, it is equal to omega 1, which is 8. Omega initially, plus alpha, it is negative 4. We found it, multiplied by the time. From that, we can take 8 to the opposite side. It will be negative 8 equal to negative 4t. So the negative will go with the negative, and t equal to 2 seconds, as you see here. It is just like the motion linear way, and it is simple to use these equations. Any question about this? Tell me, please. Okay. What is the fourth one? For the angle span until the motion stop. We know that the motion is initially positive A. Positive means the motion is counterclockwise. After a while, this motion stopped. We need to find the angle span after how many rotations? Okay, this is angle theta. This is plus omega, which is equal to 8 radians per second. I didn't talk with you, yes, I remember now, about the converting between radian and degree. Be careful that each one rotation is equal to 2 pi or 360 degrees. This is one rotation. If I ask you or I told you I have one rotation, so I have 2 pi. Okay. Okay, what is theta? We can use the second equation. Also, we can use the last equation, which is theta is equal to omega naught or omega 1 t plus 1 over t, alpha t squared. Now we need to put the time, which is 2 seconds, required to stop that object. Okay, omega naught or omega 1 is 8 multiplied by 2 plus 1/2. The acceleration is negative 4. The time, again, to stop, it is 2 squared. This will be equal 8, which is 16. We have negative. This with this is 2. It is 8. So it will be 8 radians. This is theta, simply. Five. The angular velocity and the angular position at time at several times. At this rotation, it will stop at t equal to. At t equal, we have t equal 1. We have t equal 1/2 seconds. We have t equal to 1.5 seconds. I need to find the velocity and the position at each time. So I will just solve one of them, which is the first one, for example, at t equals 0.5 seconds. What is the velocity? Omega 2. Okay, omega 2 at t equal 1/2 seconds is equal to omega naught, which is 8, plus alpha, which is -4, multiplied by the time, which is half. This is the velocity. This is the velocity, yes. This will be equal to 8 minus 2, it is 6. Radians per second. Theta at t equal half. I will use that third equation. It is equal to omega naught, which is 8, multiplied by the time, which is 0.5, plus half, multiplied by the acceleration, which is -4, multiplied by half, squared. This will be equal to, this is 4, -2, this is 1, it will be 4, -1, I think it will be 3 radians. 2, 1, yes. By the same thing, you need to change the time here, here, and here. Any question about this? Any question? Is it okay? Keep them. Okay, question 4. Okay, on tricycle, we have omega, which is the angular velocity. It is given in revolutions or total rotations. It will be 0.9 revolution per second. Revolution, it is 1 round. Just I said about it, it is 2 pi. So the velocity, it is 0.9. The revolution, it is 2 pi radians per second. Okay. If the radius of the wheel is equal to 0.27 meter, this is 27 centimeters. So this wheel, and this is the radius, and this is omega in this direction. This is omega, it's given. We need to find the linear speed, yes. The linear speed, which is this one, it is the same here. Just from here backward, as you know, the bottom of the wheel will go backward, but the velocity of all the object will go forward. We need to find the velocity. This is the tangential velocity. As you know, we have a relation. Vt. These are our relations for this. S is equal to R multiplied by theta. It is a linear distance. The velocity, it is equal to R multiplied by omega. The acceleration A is equal to R multiplied by alpha. So the linear quantity is equal to the radius multiplied by the angular quantity. Right. What's the velocity? It's R multiplied by omega. Yes, Salam. Okay, what is R? It is 0.27. Omega, it is this one. This is R, and this is omega, which is 0.9. Rotations, which is 2 pi. Radian per second. This is radian per second. The radius here, it is in meter. So this will be equal to, after putting meter in second, radian will be gone. And let me see what I 1.027 multiplied by 0.9. It will be equal to 1.5 to 68 meters per second. This is his tangential velocity or linear velocity. Any question about this? Question 5. Consider a particle rotating around an axis. Its mass is equal to 24 kilograms. Okay. This is the radius of rotation, and this is our rotation. Omega of rotation is equal to 2 rotations per second. It's the same like there. It will be 2 multiplied by 2 pi radians per second. Rotations to full rotation. And the perpendicular distance. The radius, which is the perpendicular distance from this axis, means perpendicular distance is this one. Okay, it is in perpendicular surface or plane. So R is 1 meter. Okay, okay, what we need. Find its kinetic energy. Okay. 1. We need the kinetic energy, which is equal to 1/2 mv squared. This is the linear kinetic energy. You can also find the kinetic energy, which is equal to 1/2 I omega squared. Let us find, we don't have the velocity, but we can find it. Simply, V is equal to R multiplied by omega. R is 1. Omega is 2 multiplied by 2 pi, which is 4 pi meters per second. It is 4 pi. Okay, this is 4 pi. Simple. 4 pi 12.56 or 6.566 meters per second. I have the mass, so I need to find the linear kinetic energy. Kinetic energy linear is equal to half the mass 24, the velocity, that one squared, which is 12.566 squared. This will be equal in joules. I'll square this, multiply it by 12. It will be 1,894.964 joules. This is the linear. What about the kinetic energy for the rotational motion? It is 1/2 I. We can find I. It's simple. We can assume it as a point mass. And I, in general, is equal to mr squared. Remember that? For a point mass rotating with the radius r. It is a point mass, but what if we have a cylinder, a sphere, then we have just another factor here, which is 1/12, 2/5, something like that. It is in the table. So it will be equal to the mass, which is 24, multiplied by 1 squared. It is 24 kilogram meter squared. So I is 24 by omega squared. Omega squared, it is 2. 2 multiplied by 2 pi, which is 12.566 squared. Oh. It is the same. So the kinetic energy is the same. We have just, it will be 1,894.
They always the same.
In this case, yes. In different system, we have here we don't have the look. I will tell you something. We solve like this, that another example, which is this example, which is a sphere, rotate, moving like this. There is a rotation, and there is V. In this case, we have two kinds of rotation, of motion, which is the rotational motion and the translational motion. So we have kinetic energy, rotational. We have kinetic energy linearly. Here, the particle mass is not rotating around itself. It is just rotating about an axis. Here, the rotational motion is the same as the translational motion. Okay? It is rotating, and this rotating is change in its position, which is a translational motion. Because of that, if we look at this system in an eye that need to discuss this motion as a rotational motion, we can find this energy, which is the kinetic of rotational motion. If another object small enough, like an ant here, and don't see the rotational motion and it just see the translational motion and compute the kinetic energy, he can see this kinetic energy. It is the same. In this case, our rotational motion is this, it is the translational motion. Translational doesn't mean it is in a straight line. It is just transition, change the position. Okay. Here we have two motions. We have rotational for the object, and a linear motion also for all the center of mass of that object. In this case, for example, if our total energy is 100, for example, joules, the kinetic energy translational maybe it is 80, and the kinetic energy rotational will be 20. Okay? Here we have two motions. There just we have one motion. Any question about this? Now, if the particle speed changed to be 3 rotations per second, so we have omega 2 is equal to 3 rotations. This is rotations, radian per second. So it will be equal to 3 multiplied by 2 pi. It is 18.85 almost radian per second. Now it is faster than 12. It was 12. Okay. No, it was. Where's the rotations here? Yes, it was 12. Now it is 18. We have another kinetic energy. Let us compute the kinetic energy rotational. It is the same. It is 1/2 multiplied by I multiplied by omega 2 squared. This is kinetic energy. Finally, it will be 1/2 multiplied by 24, which is I, multiplied by this, which is 18.85 squared. This will be equal to a different kinetic energy. Now we have a different speed. So it is 12. Shift answer squared, which is 4,263 point 67 almost joules. Now we have a new kinetic energy, and we have old kinetic energy. We have change in kinetic energy. From where this change happened or come or appeared or whatever you want to say. Now we have a system. Initially, it contains 1,894 point something joules. Then our system contains 4,263 point something joules. This is our system, finally, or two. What's happened to it? How its energy changed? By changing the velocity. How? We just add some work to this system and give us this energy. As you know from before, we know that the work is equal to the positive change in kinetic energy, and it is equal to the negative change in potential energy. What is the change? If I need to find the work, what is the work? Maybe this work is more power on the gas, on the fuel for the car, or we put more force or more power, more work to our system, it is 4,263.67 minus 1894.964. So our work, the work done here is just is equal to 2,368.70 something joules. This is the work done. If I ask you about theta, and you are going to find theta radians, if you multiply theta by the torque, this will give you the work, because we know that the work is equal to x multiplied by the force. But in rotational motion, we have theta in place of x, torque in the place of force. Okay. Any question? Start writing these relations on a piece of paper to use them in the final exam. Keep it clean, and you can cheat from this sheet anytime you want. It is not cheating. In the exam, there's no time to derive equations or relations. You need just to turn your mind on to apply these relations on the problem. Now we have question number 6. There's no slipping, just we have rotational motion, okay? We have this ball, which is a sphere, and this is initial position, which is position 1. This is the second position. There is a difference in altitude, which is h. H equal to how much? 0.47 meters. Okay. This ball is moving by initial velocity, which is v initially equal to 2.62 meter per second. We need this ball to climb this ramp, and we don't need any motion here. We don't care if there's any motion. So finally, if the ball climbs this ramp here, and its final velocity is equal to 0, we are okay. So we need its final velocity equal to 0. What is the linear speed of the ball when it reaches the top of the ramp? It asks about the final velocity. Yes. There is a speed on the top of the ramp. We need to find that speed. It's a mechanical energy conservation. Now we have a mechanical energy in the first position. We have a mechanical energy in the final position. So we have mechanical energy initially should be equal to the mechanical energy finally. I'll name this 1 and 2, not initial and final. This is 1 and this is 2. The mechanical energy is the kinetic energy plus the potential energy initially. The kinetic energy, we have two motions. Okay, let us give the mass. I didn't delete the mass. Right, the mass, it is not written here. It is deleted in me, it's just a table. The mass is 3 kilograms. And the radius is equal to 12 centimeters. The radius of this pole. Okay. Now we have the kinetic energy. The kinetic energy, we have two kinds of kinetic energy. We have the kinetic energy, the linear kinetic energy, plus the kinetic energy rotationally, plus the potential energy, which is mgh. If we consider this level is the 0th level, then this is not 0. So initially, now I need to compute the mechanical energy initially, which is kinetic energy, this one. Okay. Initially, the potential energy H is equal to 0. So the potential energy is equal to 0. The kinetic energy, linearly, it is 1/2 the mass multiplied by the velocity squared plus 1/2 I omega squared plus the potential, which is 0. Okay. We have the mass. We have the velocity initially, which is v1. I, we can compute I for a ball. I for a sphere. It is 2/5 from the table. The mass multiplied by radius squared. It is mr squared, but multiplied by one of these coefficients. So it will be equal to 2/5 multiplied by the mass, which is 3. The radius is 0.12 squared. It will be equal to 0.12. It is 0.01728 kilogram meter squared. This is I. What about omega? From there, the second relation here. Omega is equal to V over R. The velocity, it is initially 2.6. How much the velocity? 2.62 y is that. Assuming just 0.26, okay, 2.6, just like that. We don't need more digits. 2.6. 2.6 over the radius, which is 0.12, it is equal to. Now we have it radiant in seconds. 2.6 over 1, 2, it is 21.67 almost radians per second. Now we found omega, we found R. So the total mechanical energy is equal to half. You can see now, we need to compute the mechanical energy, but we have some parameters or some quantities are not known. So we need to find them by using the simple equations, the simple relations. All of the examples before the problems solving these equations. Now we are ready to use them in some higher level problems. Okay, the mass, how much the mass? 3. The velocity initially, the linear velocity is 2.6 squared plus 1 over 2. I, it is that small number, 728. Multiplied by omega squared, which is 21.67 squared. I will compute them like this. This is 10.14 joules plus 4.056 joules. This is all mechanical energy initially. You can see here, we have a linear kinetic energy, which is 10 point something. We have a rotational kinetic energy, which is 4 point something. The total energy, we need to add them together, plus 10.14. So the total mechanical energy will be equal to 14 point, you can consider it 0.2 joules. Now we need this mechanical energy to move to the system finally upward there, and we need to find the velocity here. Here the system, I will draw it here. Our system here contains 14.2 joules. Our system here should contain 14.2 joules. There is no potential energy here. We have potential energy here. We have velocity here. We need to compute the same relation, but finally. Okay, mechanical energy finally is equal to 14.2, which is equal to the kinetic energy, the linear one, plus kinetic energy, the rotational one, plus the potential energy. It is not zero now. This will be equal to 14.2. 1/2 multiplied by the mass multiplied by the velocity 2 squared plus 1/2 I multiplied by omega 2 squared. Now we have another rotation. Here we have omega 1. Here we have omega 2. Here we have V2. Here we have V1. Plus the potential energy MGH at the second point. Now, I'll put them. 1/2. The mass is 3. V2 squared. I don't know V2. Plus 1/2. I, it is 0. Where is it? That one. 0.1 now 0.17828. Right? Omega 2 squared plus M, which is 3, G 9.8, H, how much H? Huh? 0.47 meters. Yes, right. Okay. Here, if you look to our equation, we have two unknowns, which are omega and V. How we can find one of them, just one of them? We can use this equation. We have a relation between omega and V. As you see, V2 is equal to R, which is given, multiplied by omega 2, which is equal, R is 0.12, omega 2, V squared is equal to, just square that thing, which is 0.12, omega 2 squared. I can put this here. In this case, my relation just has omega 2 squared, right? Now this is math. Now we have 14.2 equal to 1/2. Some of you may say, I need to put omega 2 and find V. We will do that. You can say omega 2 squared, which is equal to V squared, 2/1. Just divide over. This should be squared also, because we need to square everything. Like, multiplied by 3. V2 squared, it is 0.12 squared, omega 2 squared, plus 1/2. I, it is 1.01. I am solving step by step, slowly, just to show you. Omega 2 squared plus the potential energy. We can't find it. It's just a term. It's a number. 3 shift alpha G multiplied by 0.47. It is 13.827 something. This is a potential energy. We can move it to the opposite side. From here to here. It will be negative. So it will be 14.2 minus 13.827. This will be equal to I minus 14.2. It will be equal to 0.372625 and so on. This will be equal to this. So we have 0.37. Let me approximate it like this, okay? Equal to, take omega squared as a common factor outside. And I have this 1/2, 3, 0.12 squared plus 1/2 multiplied by the rotational mass, which is the I. Yes. All of this multiplied by omega-2 squared. Now I have my equation just in one value. I will find it. It is equal to 0.3, no, 0 again. Another 0. 3024 multiplied by omega squared. This is equal to 0.37. Yes, Salam, it is very simple now. We can find omega squared. So omega squared, again, I am solving step by step slowly just to show you. It is 0.37 divided over that number 0.03 024 and something, which is equal to divided over 3 بص ناقص 1 it will be 12.235 radian. It is omega, right, per second, but it is omega squared. This unit is squared, so omega is equal to the square root of that thing. And we don't care about positive or negative, rotation or direction. We are just talking about the energy. So it is to the power to have omega is equal to 3.4979. I will put it like 3.5. I will estimate 3.5 radians per second. How much omega initially, please? Can you remind me? Omega initially here, how much is it? Okay. I what?
Yeah, we don't
No, you wrote it.
know.
Well, you need to look upward. Just okay. What about the velocity? V2. V2. I asked you about the velocity, speed, the linear speed. It is R multiplied by omega. R is 0.12. Omega 3.5. It's very simple, right? It is 0.42 meters per second. V initially, how much? V initially it was given here 2.62 meter or 2.6 meter per second. 2.6 divided over 0.2. Omega 1, it was 21.67 radian per second. Look, our system contains 14.2 joules. Its potential, so Okay. Its potential energy here is equal to 0. Its potential energy here not equal to 0 as a magnitude. Its velocity here equal to 2.6. Its velocity here, which is the linear speed, it is 0.42 meters per second. Its angular velocity here equal to 21.6667. Its angular velocity here 2.5 radians per second. This is our system. The energy is the same. It is 14.2, 14.2. It was kinetic energy initially here. It was kinetic energy by two kinds, the linear and rotational motion. The potential energy was 0. Finally, our system converts most of its energy to potential energy. And its kinetic energy comes from these velocities. Its linear speed decreases to be less than a half. Its rotational speed decreases to be 2.5 by 10. After doing all of this, we just find these things. Any question about that? Look, I know it seems to be long, but its steps are simple and short. Just you need to use the kinetic energy relation and the potential energy relation and this relation. Three relations. Any question about this? I don't know about you, but you don't need to hate physics or hate me. But when you are playing this game, you don't care about the velocity initial and finally, you are just playing. Or the bird, when any bird, when it needs to go to its nest, it doesn't need any knowledge about vectors and speed and acceleration and wind speed. Just go there and that's it. But we are complicated. We can complicate our life by our hand. Okay, what about the next question? It is nice. Let me move to, I will not solve problem number 7. We need to have some time to go to complete the next material. Okay, question 8. We have the torque. Look at me, I am a physicist. I just care about that. I understand the problem, okay, yes. But the important thing are the quantities. The torque is 15 Newton dot meter. Again, Newton dot meter is not Joule. Oh, it's a good question to ask. We apply a mechanic. We have the radius is equal to 35 centimeters. I converted directly to meter. What is the force? The force is RF, the torque, sorry. RF sine theta. I didn't give you any theta here, so you can assume theta is 90 degrees and sine theta is equal to 1. From that, I need the force, which is equal to torque over the radius, which is equal to this over this. 15 over 0.35, which is equal. This is newtons over meter over meter. So meter will cancel with meter. The unit will be just newtons. So 15 over 0.35 observation. It is 42.857 something newtons. Right? Simply. You can add this to this. We have the torque is equal to the radius multiplied by the force. Question 9. We use this system many times in our life. If we have to remove any mass and we have this system, we have, this is the point of rotation, and from here to here, we need to remove a planet, and we have this distance, which is we have it 0.04 meters. I convert it from centimeters to meter. And the force R, we can name this the arm of the resistance, which is the thing we need to remember. And this arm is the force arm is 22 centimeters. And the the torque applied here is equal to 1.07. Why is 0.7 here? Okay, what is the force? Calculate the force. Okay, the torque should be the same, the both sides. The torque to remove this planet should be applied by our force by using this arm. Should be equal to the radius multiplied by the force by sine theta, which is should be 1 if we apply our force perpendicularly to this arm. So the radius is 0.22. The force is unknown. The torque is 1.07. Remove 0.7. We don't need it. So the force is equal 1 over 0.22 centimeters, which will be 4.545 and so on newtons. How we can know that? We need to remove this. We need to apply a torque, and we need our motion to be without any acceleration. So we have equilibrium about this point. So the torque from the left should be equal to the torque from the right. And because of that, we found this. Question 10. We have this system. This is 9 kilograms. This is 1.2 kilograms, 2.5 kilograms. This distance is 1 meter. This distance is 2 meters. Yes, what do you need? These masses are connected with light rods. Light means there is no mass for this rod between them. We have X, Y, Z. We have a mass here, and a mass here. This is X, Y, and Z. We have an acceleration, angular acceleration, which is alpha, equal to 1.6 radians per square second. Can I take some rest? Okay, now our system, L-shaped system, is rotating. We need to check 3 types of rotations. First one of them around X, then around Y, then around Z. And we need to find, I think, the torque, or what? What torque must apply to rotate this system by this acceleration? Now, look, if we need to rotate it about X, this is X, going out from the torque. The torque is equal to I multiplied by alpha. Alpha is given. I, we have more than one I. Remember from previous studies, we have the total force is equal to mass 1 multiplied by its acceleration, A1, plus mass 2 multiplied by its acceleration, plus mass 3 multiplied by its acceleration, and so on. And we have the same thing here. We have the total torque is equal to that. First, let us name them. This is 1, this is 2, this is 3. 5. So it is equal to the first moment of inertia, alpha 1, plus I2, alpha 2, plus I3, alpha 3. We have now point masses, just like that. The point mass, we need to find its moment of inertia, it is equal to its mass multiplied by the radius squared. Radius, it is the distance from the axis of rotation. Okay, I1. The axis of rotation, it is here. The mass is 1.2. How much are, if we are rotating here, how much are the radius? How much is the radius here? How much is the distance of the mass from X equal to 0 here? It is 0 squared. So I equal to 0. What about the second mass? This is R, it is 2. I2 is equal to 2.5 multiplied by R, which is 2 squared. So it is 10 kilogram meter squared per unit. What about I3? I3, I'm talking about the rotation about X, about the point 1 here. The mass is 9 multiplied by 1 squared, it's equal to 9. Okay, what is the total torque? Now, required to rotate them by the same alpha. alpha should be the same. So we don't have 1, 2, 3. We have it the same alpha. It is I1 plus I2 plus I3 multiplied by the same alpha, which is a common factor. Alpha, it is 1.6. Okay. Now, I1, 0, plus I2, 10, plus 9, I3, multiplied by 1.6. And it's simple. This is tau about x, the x-axis, okay? So it will be 19 multiplied by 1.6. It is 30.4 Newton meter. It is not work, not joule, okay? This is about x. This is about x or Ix. Now, if we need it about y, this is y. We need to rotate like this. Now, about y, all of them are simple, okay? But you need just to stop and start solving again. What about I1 for the first mass? Its mass is 1.2. How much its distance from y, which is this one? Because x is going out from the board. The distance from y is 0, so I1 is 0. What about I2? The mass is 2 kilograms. The second mass lies on y. So its distance from y is 0. What about I3? It is 9 kilograms and its distance of rotation about y is 1 meter, like this. 1 squared, so it will be 9. Simply now, the total torque about y is equal to 0 plus 0 plus 9 multiplied by 1.6. It is equal to 9. It is 14.4 in Newton meter. Is it simple? Okay. What about Z? This is Z. This is Z. You can see the third mass, the first mass lies on Z. So I for them is 0. Okay. About Z, I1 is equal to 1.2 multiplied by 0 squared, it's 0. I2 is equal to 2.5 multiplied to rotate like this by 2 squared. So it is 10 again. I3, it is 9 multiplied by 0 squared, it is 0. Because it is on Z. By the total torque about Z, it is I1 0 plus I2 10 plus 0 multiplied by what? I what? By yes, the acceleration. Thank you. So it will be 16 Newton meter. It is just the relation between the force and the torque and the moment of inertia. The moment of inertia again, it is the mass or the, I think you saw that in the questions, the quiz or the homework. The moment of inertia is the rotational effect of the mass. Okay. It's a long lecture today, but it is important. Okay, 11. long posture, but it is not. Let us draw our system. And we have another we have the string A, we have a tension force here. We have a tension force here, string B, TB, TA, and we have a mass here, M2, and this rod has mass 1. Its length is L equal to 5.6 meters. It's a crane. M1 equal to 75 kilograms. M2 equal to 3,000 kilograms. This is the requirement that frame. D is the distance from the mass to this place. No, this is X. This is D. How much X? 5.4 meters. Okay. What else? We have D equal to 1.1 meter. Okay, now we have everything. Look. We have a crane. The rod has a mass, which is 30 kilograms. The mass is 75 kilograms. Its length L is 5.6 meters. It can carry a mass of 3,000 kilograms. We can put this mass at a distance 5.4 meters from a point of this center, and there's a string, another string at point A here, a distance D from that center, which is 1.1 meters. So this crane can lift things far away like this. This string, this crane is fixed at this point and at this point, like this. And we can put masses here. And we can move it like this and like this. Okay? We need to compute some quantities for this system. Again, it is simple. G, as you know, it's 9.8. Find the tension in A, find the tension in B. Okay. I'll draw it like this. This is the point A. And this is the point B. First, we need to find TA. We have TA upward. Yes, upward. We have a mass here, and its weight downward, we need to name it W2. We have also the weight of that rod, which is M1. This rod is uniform, And we can consider its mass at the center of it, which is here. So we can consider W1, which is the weight for this rod at this point. This weight is equal to M1 multiplied by G. This weight is equal to M2 multiplied by G. We can compute that. So now, this is the center of rotation. We have three forces, TA, W1, W2, at a different distances, okay? Here, we have it. It is X equal to 5.4. At this point, look, the length of the rod is 5.6. The middle, or the middle of that point, it's 5.6 over 2. We consider its mass as a point mass at its center. Here, the distance is 1.1. Everything is given. We need to find that one. We have three forces. Let us find the weight here. M is how much the mass? Yes, for M2. This is M2. It's 3,000 multiplied by G. Here, it is 3,000 multiplied by G. It is equal to 29419.95 newtons. What about this one? It is 75, which is M1, multiplied by G, shift alpha G. This will be equal to 735.5 newtons. I approximate it. I will approximate this also to 20. Okay. Okay. Now we have rotational equilibrium, means the total torques equal to 0, which are equal to the torques counterclockwise plus the torque clockwise. Okay. 0. The torques counterclockwise, we have just this one, which is TA multiplied by its radius. We know that the torque is equal to the radius multiplied by the force. And all the angles are 90 or 20, 270. .1, this is counterclockwise, plus from the first weight, which is 735.5 multiplied by its distance, which is 5.6 over 2. It is clockwise. It will be negative now. This is positive. Plus 420 multiplied by 5.4. This is clockwise, which is negative. So we have two negatives, one positive. Okay. So 0 is equal to 1.1 TA minus these two quantities. Minus eight 735.5 multiplied by half multiplied by 5.6 plus in this the 5.4 aha minus 160,927.4. This is equal to this. Okay. Now move this to the opposite side. Divide over 1.1. So TA will be equal to 146,297.637 almost newtons. Now look, the weight of the object, what we lift is yes, 29,000. The weight of this object is 29,000. But the strain or the tension on this string is 146,000 and more. So we do here, we are doing more force to lift this object at far away, just like the muscle here. It applied a strong force just to lift a book here. And we compute that 7 to 8 times heavier than that book. And also here, if you multiply by 7 or something like that, there's a ratio between them. This is the tension on A. What is the tension on B? Now, we need the tension here on B. It is the same thing, but we need just to change our origin. We are now here at this point, our origin. This is B. We need just to change our point of reference to be here. Okay? So our system will be like this. We have the weight here. We have another weight here. We have another tension here. We have the total tension, which is equal tension counterclockwise plus tension clockwise should equal to 0. This is negative, this is positive. The weight here, we know the weight. It is equal to, I said it is 29,420. This weight is 735.5. We need to this. This is unknown. Now we need the distances R. We know this is 1.1. From before, be careful now. You cannot use this distance as this distance. This distance is from B. We need it from A. So we need to remove this part from this. So the distance from here to here, it is 5.6 over 2. 5 over 6, it is 0.2, it is equal to 2.8. Okay, so this is 2.8 minus 1.1. What about this distance? Okay. 5, what?
5.6.
Where is it? This is 5.6. We need this one. This is 5.4 minus 1.1. Be careful about this, okay? Now we have the forces, we have the lengths. So we have another problem. Okay? Can I solve it here? I will see. So we have 0 equal to counterclockwise, which is B. B is counterclockwise. By its length, which is 1.1 T B plus, we have minus quantities there because they are clockwise, as you see. We have why they are minus, because R, this is R, and this is F. The angle between them is 270. Sine 270 is -1. This is the negative sign. Okay? So we have R here is 1.7 multiplied by this force, 735.5, plus, we have a minus sign, remember that, plus, this is the minus sign because we have clockwise. The distance is 4.3. This minus this, multiplied by this force, 29,420. These are negative. This is positive. Move this to this side, it will be positive. Divide over 1.2, 1.1. So B is equal to something divided over 1.1. I will tell you what is that something equal to. 1.7 7 3 5.5 plus 4.3, yes. And okay, it is equal to 127,756.35 over this. So TB will be equal to 116, 142, 136 something newtons. Now look, we have a tension in the string A, which is 146. We have a tension in string B, which is 116,000 and something, okay? So the tension in string A is more than the tension in string B. So when you are an engineer and you need to construct and build this crane, you need to put strains or rods. You need to put this rod heavier and stronger than this one. Because of that, you can see in the crane, there are big rods and thick rods and small one and so on. That depends on the torques and the forces and the strains on that part. Is that clear? Do you need more? You can solve the rest alone, and if I have a time, I will solve them and I will report the solution. And in today's lecture, you have 3 problems are unsolved. You can solve them by yourself. As I told you, just prepare your formula sheet. If I can, I will do it for you.